So then use Hall probe, investigate magnetic flux density. When you see this thing, Hall probe, investigate magnetic flux density, you should already think of this one is a B field, a magnetic field experiment. This is not an induction experiment. What is induction? Later we will look at induction. Not induction experiment, B field experiment. Use Hall probe is B field. Magnetic flux density, B field. Induction, we measure different things, we have different goals. Anyway, we have this electromagnet, a coil, iron core. Point P, equidistant. Equidistant means you need to figure a way to make sure this thing is same distance and then this one come down like that. Oh, how to do? I don't know. You find out. Okay, and the poles of the magnet here refer to this one, pole 1, pole 2. Distance P is vertical between the P and top of magnet. Flux density at point P is some B. So you are trying to measure at point P, what is the B? Then they give you some equation, B, kNIe. What are the things you want to change? Firstly, if you didn't underline this, design experiment to using a Hall probe to test the relationship between two variables. Every question one will mention this. Test the relationship between these two. So you're going to change one of these and measure the other one that changes in response to your change. Your independent and dependent variable. P is what? P is the length. Yeah, that one use ruler also can. Now the B one is one you have to use Hall probe. Okay, and eventually you want to explain how you can determine values for alpha and k. So make sure at the end of the experiment you give your equation. Alpha equals to gradient times something something something, and k equals to something something something. You have some equation there. This is the first scan. When I just read through, I'm already making note of what I need to do at the end. But I'm going to focus more on the setup. Because if you can set up and know what's happening, the rest is just a matter of writing. Let's go and see the setup. First question for you to think about. Actually, why we put iron core? No need iron core also can ma. Why put iron core? No need iron core also can have magnetic field. What? Why bother? That is the question you need to answer in paper 4. Why do we use an iron core? But anyway, let's look at this. We want to measure B. That's the main player, B. To create a magnetic field, we need to somehow send current through this coil. So you need a circuit. And you must draw the circuit. Some people didn't draw circuit. I'm like, where your magnetic field come from? Magic, thin air. No lah, circuit. So make sure you draw some kind of circuit. Now what do you connect it to? Should we connect to AC or connect to DC? In this case, you want a magnetic field measured by a Hall probe. Do you need to induce anything anywhere? No. It's just one coil. No this is not an induction experiment. So we do not need AC. We are just going to do DC. So I'm going to put the battery here. Something like this. And I want to kind of monitor the current as well. So maybe I put a ammeter here to keep an eye on the current. Or if I want to change the current to something suitable, maybe I put a variable resistor right here just to control it. Or you can say DC power supply also can. It has all this function. But better to draw everything. Now this coil, if you keep letting it run for a very long time with the current going through it, like this, there's a problem in the coil. It might get hot. Heat. So how? Make sure you wear gloves as a safety precaution. Or also can add a switch here. When you're not using, you open the switch. When you're using, you on the switch. Then it will have a magnetic field. So this circuit is to generate the field. Just a steady field is enough. If you're asking me, why cannot AC? Can, but you have a lot of problem in experiment because of induced current here, induced current there, and it's just not good for experiment where you want to use a Hall probe to measure B field. So this one will be DC, power supply. You will only use AC if you want to induce experiment to measure EMF. Here nothing mentioned, no EMF, nothing. Okay, so we don't go to AC, don't go to AC. Okay, next. So this is one coil. How does the field look like? I'm just curious. We can draw it out actually. Use your right hand grip rule. You will realize that this is a solenoid. So the field kind of goes up like that. If let's say the current is this direction. But why got iron core? You see, without the iron core, it's just a coil. The field won't be as strong. But once you put the iron core will become part of the electromagnet, become magnetized, and make the field much stronger, many times stronger. But actually, this solenoid field looks like this one. You don't need to draw this in the experiment, but I'm just showing you how the full solenoid field actually looks like. It's like this. And the iron core will help to guide and strengthen all these flux lines so that it is measurable at B. It's quite strong at B. Okay, something like that. I think this is pretty good. Okay, so next thing, we want to measure B at the point. How to measure Hall probe? How to draw Hall probe? Where to put Hall probe? You can either put it like this, front view, up at point P, or you can put it side view, like that, and face that. Doesn't matter, I mean, you want to put wherever you want to just put. So I'm going to put it front view, side view, also can. Usually what I'll do is, I'll put a little square here to show that, oh, that's a semiconductor in the Hall probe. But Hall probe can't be floating. Remember, we did experiments in class, you need a retort stand to hold these stuff. So make sure you have a retort stand. I'm going to draw that later, or maybe I should just draw it now. Retort stand. Hall probe must be connected to this thing called a voltmeter to measure the voltage. I'm going to pause here. And last week I wanted to show you guys how our phones have Hall probe. How Hall probe is like our phones, right? So you grab your phone or you look at it, it's like flat. It has like a camera there on one side. Okay, and you're going to rotate the Hall probe until you get maximum reading. But what actually you see is only the voltmeter reading here. So this is only like some, I don't know, 5.6 mil volt. That's not magnetic field. You want to measure magnetic field. So you need something to convert this 5.6 mil volt to something like Tesla magnetic field. How to convert? This is what we call a calibration process. Calibrate with what? Calibrate with a known field. So whenever you say Hall probe, you must calibrate with a known field. Known field means what? Means let's say you have a solenoid. And you have an equation for the solenoid. B equals to something, 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 NKI. I can't remember what is it already. Go and check your notes. So you take the Hall probe, you put it in here, and let's say you get a certain number. Let's say 2 mil volt. And when you use the equation to calculate for your known field, you get a magnetic field of 2 millitesla. So you know, oh, when it's 2 millivolt, it means 2 millitesla, and you can plot a graph of B against V, or the other way around, I suppose. Such as here and here. That is the whole process of calibrate. Because your Hall probe only can show you mil volt, but you want Teslas. And we know there's a relationship between Hall voltage and magnetic field. This one is in paper 4, theory part, where this equation comes. So you put in here, you're going to see readings, calibrate. I always tell you guys, calibrate number 1. Number 2, rotate until your Hall voltage is maximum. So this thing you got to rotate. Rotate, you find maximum now. Okay, then you stop. Lock it there. Tighten with the retort stand. It may be at some angle, but the idea is you want the magnetic field to be perpendicular to your Hall probe. So chances are it will probably end up to be sideways like that. Then the magnetic field can go right in, perpendicular, and come out. That's when you have maximum reading. The reading very small. That's why I want to make it as big as we can. Okay, what else do we need to add to our diagram? Now, okay, we think we got our measure B pretty well. We need to measure distance, P. So I'm going to rub off this field a bit. So we have some space. Notice this experiment, the diagram very crowded. Many things to draw. How do you measure P? There are a few ways to do it. I noticed some people have different ways of drawing it. Some people, okay, we need a ruler. Where to put the ruler? Big ruler. Okay, big ruler here. Some people put the ruler right here. Can also. Some people put the ruler, instead of sitting on the iron core, it is touching the table like that. Can also. Some people say, Miss, this part too crowded already. Can I put the ruler outside here? Can also. I'm fine with either. Let's say we want to put it here lah. From the table up. Actually, it doesn't matter. Just put lah. Okay, let's say I put here. This ruler will measure two things. You can find the distance up here, the distance down there, and subtract both reading on the ruler. That will be your P. Right? That's the first thing for this ruler. But another question is, how you know your ruler vertical? Maybe your ruler tilted there. Oh, you need something to make sure this ruler is vertical. So maybe put a set square or spirit level. Spirit level can also make sure ruler is vertical. And of course, clamp it down. Once you check vertical, clamp it down. Last thing, how do you know this hall probe is exactly in the midpoint? You see these two lines here? Line, 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 line. How do you know this exactly in the middle? Have to put another ruler. Oh, okay, put another ruler. These are additional detail already lah. So if you manage to think of these, then that is extra marks for you. It's good to be worried in experiment. What if this one? If you got that one, then how? Then what? So all these worries will translate into additional detail. So maybe I'm going to put the ruler like this. There's no space already. I can put here lah. Okay, sure, put here. So I can calculate where exactly how many cm is the midpoint. But I need a way for this hall probe to mark the middle. So I'm going to use what we call a plumb line. Plumb line means the position where the hall probe is, let's say behind here, I hang this very heavy string, metal string, where it has a very heavy metal at the other end. So it will always be straight lah, vertical all the way down to earth. This is what we call a plumb line. You can Google it. A lot of people in construction and engineering, they use this plumb line to make sure things are vertical. Is the wall vertical or not? Use a plumb line. Hang from the top. See whether the line aligns with the wall. So this is called a plumb line. Then you can see, it passed through the middle here exactly. Very good. Done. So this one, gotta do all the labels. This diagram is complicated. Ruler, coil, set square, plumb line, hall probe. Oops, didn't label. Hall probe. What else? I think that's it. Looks good. Okay. So this should be, if you want what we call a good diagram, you should have a lot of these things, or most of these things. I think everything clamped down, hall probe, ruler, set square, everything else. Okay. So if you haven't drawn this experiment, then you can use this as a hint to help you think of the details involved in the experiment. Maybe the first time you do, you're like, me, so many things to remember. Well, over time, you build your experimental knowledge. I'm going to draw a retort stand. Okay, so from now onwards, you just have to change the distance P by moving this clamp, change up, change down, and measure B, which is on your voltmeter or hall probe lah. Okay, so that's all for this experiment lah, the main part of it. How do you set up something like this? Yeah, there's a lot of things to draw, lots of things. Now, question is, back to the main thing. Is this a magnetic field experiment, flux density experiment, or induction experiment? Nothing to do with induction. We do not want a changing magnetic field. It's going to cause eddy currents everywhere, and it's just not good for the hall probe. Hall probe is very sensitive one. Mu volt, so small. Any kind of fluctuation, you sneeze also, the reading can change. So that's why we use a DC power supply. So this is what we call a magnetic flux density experiment, a B field experiment. This is not an induction experiment. So that means, what if it's induction experiment? How would it look like? How would you change this experiment to become induction? Do you think for a moment? How would you change this experiment and turn it into an induction experiment? So characteristic of a magnetic flux density experiment is like this lah. Let's go and see. I don't know if this already exists in paper 5, but I'm going to create my own experiment using this exact same diagram, and you will see how these two concepts are related but not the same. Wait, I'm getting there. I just need a diagram. So if you replace the Hall probe with a coil, then it has become an induction experiment. Let's see. I'm going to write, I'm going to paste here. Exact same diagram, but now instead of measuring B, E, and P, I want to study something else that involves the induced EMF. So, yeah. Why hang now? So instead of studying B and P, I want to study. This marker does not want to go away. Come on, you can do this, computer. Alright. You want to study not B and P, but maybe induced EMF, V, and something else. I don't know. Frequency, current, anything. Could be a whole bunch of stuff. How would I turn this into an induction experiment? Well, first thing I could do is maybe replace the Hall probe with a coil. This Hall probe originally was intended to measure B. But now if I say, I want this to be an induction experiment. Okay, how do we induction? We can put a coil here connected to a voltmeter. Ooh, what's going to happen to the coil? Now, if you want to be an induction experiment, you need to have a changing magnetic field. Now, this we're looking at the induction experiment. Means the difference between this now and this one is now you need a changing field. So here you have to put AC power supply. You want to maybe monitor the, if you want to monitor the voltage or something, put a CRO in parallel. Or if you want to measure ammeter, okay, put everything, I'll just draw everything. Ammeter, this thing, variable resistor, all just draw. AC circuit, just draw. The main thing is AC. So now your current will flow back forward. Then one moment it flows backward, keeps changing direction. So you have a field, yes, you have a field, but it keeps changing direction and there's always some kind of change in flux. So when you have, how do you identify an induction experiment? Firstly, they will ask you to measure induced EMF or some kind of V. Or you have a changing field, this one, and another coil, either up here or wound on this side. So you have a primary coil that creates the field. This coil creates a changing field. And the other coil will have induced current because of a changing field through this second coil. So if it's the one up there, you see the lines passing through it, right? That line is changing. Magnetic field is changing. Changing in strength, changing in direction. And if you have a secondary coil on the right, you see the lines here, the linkage, the flux, all changing. So what you need to do if you have an induction experiment is you must connect a voltmeter. I mean, if you want to measure the voltage, induced EMF, you measure voltmeter lor. If you want to measure current, then you connect ammeter lor. It depends. You have to read the experiment. So this one is to measure induced EMF. Measure induced EMF. This is, by the way, what we call a transformer, where you have an iron core and two coils wrapped on either side. One coil, solenoid coil, creates the field. The other one just feels the field passing through it and have some induced current to oppose the change. This is in chapter 23 and 24 as well. Okay, so see these two experiment. Same diagram, but I can change a bit and then become, one is magnetic field, one is induction experiment. Induction, you use AC. Magnetic field, try not to use AC. DC. Because the problem of eddy currents everywhere. Okay, give you a stare at this thing for a moment to see the difference between both of these. Okay, be clear. What questions do you have about this before I go and find an actual one that kind of can confuse people? In induction, do you need to put point P? It really depends on the experiment, but usually if you were doing induction, why would you want to measure point P? I guess you could also lah. You change P and you see what is the induced induce EMF. Can also lah. It depends on experiment. It depends what they ask you to find. So, ooh, you see how you can start to create experiments? What if you see the relationship between P and frequency of the AC? You create experiment to study that. What if, how does the number of turns of this thing affect the induced EMF? So you can study number of turns against induced EMF. Can also. You just pick any two variables and create an experiment out of it. That is what scientists do. You think, oh, what if this? Change and see. Oh, what if like that? How is these two related? Okay, then you play with those variables. No relationship. How about these two? No relationship. So you're basically just kind of testing all the variables and see how they relate to each other. Okay, I'm going to show you one experiment, like two literal experiments. I won't discuss through the whole thing, but I'll show you the diagram, how they are exactly the same setup like this, but they are completely different things they are studying, different circuits to draw. You may have done it before already, but let's check it out. Okay, the first one is in your page 4. ON17 P52 Q1. Look at this coil. Okay, let me open another one. It's on page 4 of your P5 set B. Then I open up another one, and this will be S14. P52 question 1. Two coil also. I mean same experiment. Oi, look at the equation here. B equals to something something something. Then you look back at the other one. V equals to something something something. Oh, oi. This looks the same, but it's not the same experiment. Let's screenshot both and look at it side by side. So if you've already done the is set 4, I think, Q1 set 4. If you've already done it, then you will see the difference in both of them. So the first one here is ON17 P52 Q1. Spot the difference. We can play a spot the difference game. The other one is MJ14 P52 Q1. So these are the two types, basically the two types of experiments of magnetic field that can come out. It's either induce or you induce or just measure magnetic field only. Maybe they can give you both. No. Let's see. Alright, there it is. Look at this beauty. Both the same. Looks the same. Very different experiment. So I'm trying to keep this as big as I can so we can see everything. If it's too small on your phone or computer, you just zoom in lah. Pinch to zoom or use your computer to mouse to scroll or touchpad to zoom. Okay, I'm going to keep it here. Left side. What's the two variables you're studying? Look very carefully. Test the relationship between V and X. This is the line that I always ask students to underline because that will tell you what are the two variables they're going to play with. The rest we try to keep constant. So let me see. Test the relationship between V and X. What is V? EMF V induced. Oh, this is an induction experiment on the left side. How about on the right side? What are the two things you're studying? You look for that sentence. Test the relationship between B and R. Oh, that's completely different. You're just measuring B. So on left side, you will need EMF induced. Need induced EMF means you probably need an AC coil, AC current. So one coil will have to generate the AC. So if I draw a circuit, if you check whether you draw this last time, one coil will need some kind of AC. Very high frequency. Oh, you need to measure frequency. Okay lah, put CRO. What else you want to put? I might as well lah, put ammeter, put Weber resistor, everything there. So this is AC. On the other side, there will be induced EMF. So you want to measure that, right? So you put V. How about on the right side? Let's go to the right. You want to measure magnetic field or magnetic flux density at the second coil. Oh, test the ratio between B and R. What is B? Look for B. Magnetic flux density at point X. Oh, so this one will create some kind of field, these two Helmholtz coils, and you want to just measure flux at B. So you put a Hall probe here. Like that. Means the left side diagram don't need Hall probe. No, we don't care so much about the B. We just want to know the induced EMF, so we don't need a Hall probe. In fact, I don't know if your Hall probe will like an AC field or not, because it keeps changing. Okay, so the main thing, oh, you notice this? They help you to connect these two coils together already. Because both coils should have current in the same direction to create that steady constant field. So maybe something like this, current. So you just need a DC. What else you want to put? Put variable resistor, put ammeter. All these magnetic one, you put variable resistor, put ammeter to either monitor the current or adjust the current. Spot the difference between these two now. Left side is induction experiment. You are inducing an EMF in the coil. The field is the same, but only one fella have the field now. This one down here. This one on the left have a field that looks something like this. And this field extends to the other one, causing a flux. But if you look on the right, both of them work together to create a stable field, a constant, unchanging magnetic field. Of course, you will move them further apart. But there are differences between these two. Okay, so the left side is induction, right side is just a flux density experiment. So I'm just going to put this a B field experiment. You are studying the field and what affects the field. On the left side, you are studying induced EMF and what affects the EMF. There. This is the whole summary basically of chapter 22 and 23, side by side. So whenever next time you all see some magnetic experiment, they're pretty common. Make sure you check, is this induction or is this just a magnetic field experiment? Because your circuits will be different and the tools you use will be different. This one no Hall probe. This one got Hall probe because you want to measure B. This one you just measure induced EMF with your V, can already. Last thing to show you. There's a pass here for this. At first I want to use it as a quiz, pop quiz. Then I look, no lah, this one. So many people ask me this question already. No lah. See if I can find it. Give me a second. In the meantime, you all stare at this one first lah. Make sure you note down difference between induction, the two types of experiment. How do you tell? This one. FM, no, ON. Okay, let me go pull it up. While you all stare at this first. I'll just show you lah. You want to go try, you go try lah. Or maybe you already do. So we're going to look at ON18 P41Q9. Is this correct? Oh, ON18 P42 Q9. Now this idea of whether you can tell what is what, whether is it induction or is it B field, is also useful for you in paper 4, not just in experiment. Experiment, yes, you need to know the setups for that. But also, you look at this one. I'm going to screenshot this as well so we can look at the big picture, compare together. In the first part, they say, put a Hall probe, everything. So I'm going to paste that in. Give me a second. Left side, I'm going to put ON18 P42Q9. This one is like the examiner say, I'm very sian. I design question until sian. Okay lah, we put both together. Induction and also magnetic field. Both together. So part A, you read the question. Put a Hall probe there in the coil. Measure magnetic flux. Pretty straightforward. Then you go to part 2. Still the same experiment. What's different? Spot the difference. It's a different thing. Different experiment. So on the left side, they want you to draw a graph of B against time. On the right side, they want you to draw E against time. I'm gonna post. Wow, it's a lot of graph. Okay, I screenshot everything lah. Everything. There. This is two parts to a question. ON18 P42 Q9. They look almost the same, but they're actually different things. On the left side, pay close attention to this. What are you measuring? Why is there a Hall probe? What is the Hall probe for? Hall probe purpose is to measure B. Then it's on the current. Oh, got current, got magnetic field, so your Hall probe can measure something. Okay, sure. And you can vary the magnetic field strength. So it's like that. Oh. And then from the magnetic field, they ask you to draw the Hall voltage graph. So this is all studying the magnetic field, mainly the field B. Then you look on the right side. What did they change? The Hall probe is now replaced with a small coil of wire. See this tiny little coil there? That's your coil there. Ooh, we have two coils. This is going to be an induction experiment. I can smell it. I can feel it in the air. And it's connected to a sensitive voltmeter. Why do we connect a voltmeter? This voltmeter is to measure induced EMF. Whereas the original voltmeter here is to measure the Hall voltage. There are two different effects. This Hall voltage, by the way, is not induced. So now you are going to have a induced EMF in this small coil. When you vary the magnetic field from however lah, you can vary in a certain way. So now they just simply they just change on it lah. So you say, miss, but this one is DC. Well, DC can do meh? Can. Why not? Sometimes we use AC if you want a consistent consistently changing magnetic field. But now they want to make your life easier, so they don't give you like a magnetic field that looks like this lah. It's not very hard to draw graph there. You also have to do like this. A bit hard, a bit high level. So they say, okay, we'll make it a little easier. We just change instead of forward, backward. Instead of an AC, we just give you a DC that is changing. So at first very high, then you change direction, low. So they manually change the DC though. It's kind of like AC already lah. But AC is like this. A bit hard to sketch. So we're like, no. For students, we don't want to kill them. We want them to be able to show their understanding. So we do this. Okay. So from here, you have a changing field, this part. Highlight here. This section, there is a change in field. So when you got change in the flux, then you got some induced EMF in this section. And then you have to draw it out. Okay, there are quite a few questions like this where they have a Hall probe, then they take it out and replace with a coil, and then it suddenly changes from magnetic field experiment to induced EMF experiment. So make sure you know how to do that in some of those. At first, I was going to give these guys to you as pop quiz. Then I decided, not it lah. Draw graph very hard if you are remote. And like you have to take a paper, draw graph. But I recommend if you have your handout, go try it out if you haven't. This is, what page is this? Where is this? This is in the chapter 23 handout. Page 23. Oh, chapter 23, page 23. Very nice. Okay. Yeah, I think it's good. All right. So that's the whole main idea of today. I mean, not today, the first part of today. Make sure you can tell there's magnetic field and there's also induced EMF from a changing magnetic field. And experiments can be a bit different. Setups in questions can be a bit different. See the difference? These two, I look at it, I'm like, these guys, this Cambridge is just lazy to create new diagrams. Anyway, different setups. This one, I just created my own one. Oh, maybe I can give it for a test or exam. I don't know. Maybe no lah. Since I already tell you I won't use it for a test. I can just take any magnetic field and change it into another type. So this one, left side, a lot of diagram. Magnetic field, I'm going to study that. If you change it to a right side, you have two coils, either this one and this one. Or three coils also can, no? But a bit extra lah. Then you induce an EMF that you want to measure.